Good afternoon, everybody. Welcome to another hot, humid afternoon of Chem 170 with your host, me, Dr. White. Seriously, be careful out there. It's been hot. In fact, one of my former students who is a fireman paramedic surprised me when he shared something a while ago that when it's cool out and very humid, it's just as dangerous as when it's hot out and very humid. In fact, that people don't realize that and push themselves too hard when it's humid but cool, and they get serious medical problems. You can do that too when it's hot. All right. Public service announcement from me, Dr. White. Don't forget, tomorrow, and let me go to D2L to show you. Tomorrow, after class, I will be sending out the password for the password protected PDF file that's in D2L now for test number 1. You'll take it on Thursday or Friday morning. Test number 1 has 10 pages, 14 problems. Some of the problems have multiple parts like A, B, and C, like my practice problems do, but they're no multiple choice. It covers alkanes, cycloalkanes, I should have also put there, alkenes, alkynes, and aromatic compounds. Here's the breakdown. General knowledge, 13 points, like how many bonds to carbon? 4. And nomenclature, you know what that means. Here's the molecule, give the Iupac name. Here's the name, draw the molecule, and then reactions. Give the product or products, except for one problem will be give the starting material. I'll do another one of those today. Like I said, tomorrow after class, immediately after class, I'll send out an email to everyone with the password for the password protected PDF file, which you should download. You'll have until 11 o'clock Friday morning to take test 1 and upload it. When I send out the password, I'll remind you, take about an hour, hour and a half to do the test, and don't count as time taking the test when you do your, either take a picture or scan it and upload it. That's separate. That's why I'm giving you all that extra time. Let me switch to student view and D2L. If you click on assignments, you'll see right there, test number 1. Now, if you don't have a printer, you do not have to write out the problems. Just print your name on the paper, print like number 1, question number 1, and then just a number, not the whole what I put down on the piece of paper. If you don't have a printer, and then write your answer. And don't forget, here's a way if you don't have a scanner, and here's another way how to create from like a cell phone pictures, a PDF file, which you can then upload. Let me do this. All right. Now, before I continue, there's one other thing. If you go to D2L, and I talked about this yesterday, click on lectures, which you see here, and you scroll all the way at the bottom, and you say, wait a second, Dr. White said the review is there. It's not. You have to click on this button at the bottom where my cursor is, at the bottom, that says load more, and then scroll down more, and you'll see test number 1 review, both as a Word document and as a PDF document. So let's get going. What I like to do now, and thumbs up people, can you see test number 1 review on your screen? Thank you. All right. And let's begin. You should know, thank you, Jimmy. You should know what are hydrocarbons? And those are molecules with only carbon and hydrogen atoms. You should know, hint, what is a saturated hydrocarbon? Because a hydrocarbon, it's a molecule with only carbon, hydrogen atoms, which all carbon-carbon bonds are single bonds. Next, unsaturated hydrocarbons, and those are molecules with only, again, a hydrocarbon with only carbon, hydrogen atoms. And because it's unsaturated, it contains one or more carbon-carbon multiple bonds, being a double or triple bond. Now I have here definitions for alkanes and cycloalkanes. I won't ask that on a test, but I might put that in a question. Draw an alkane or cycloalkane, and you should know what they're talking about. All right, speaking about drawing, you should know, and we went through this, how to draw alkanes and cycloalkanes. In alkanes, you show the carbons and hydrogens, and don't forget, your friend on test 1 is how many bonds to carbon? 4. Oh, I'm ambidextrous. How many bonds to carbon? 4. So remember, 4 bonds to carbon. And we went through this. Now, went through the nomenclature rules, Iupac rules, for alkanes and cycloalkanes. And the first thing you need to know is how to determine the longest chain. Once you do that, if you have branching, first you name that as an alkane. And we went through, and hopefully you know the chart for the alkane names 1 through 10, methane through decane, 5 is pentane, 7 heptane, 9 nonane, etc. Also, you should know the alkyl groups. 1 carbon attached to something is a methyl group. 2 carbons attached to something is ethyl. 3, you have 2 choices. If it's to the end carbon of 3, it's N-propyl. If it's to the middle carbon of 3, it's isopropyl. Next, we have 4 carbon alkyl group. And here, if it's to the end carbon, it's N-butyl. Now there's one I'm at to the second carbon. I've never seen that, so I'm not going to teach you that. But anyways, and the other you should know is 3 carbons attached to a center carbon, which is attached to a ring or something right here, and that's the tert-butyl group. All right, now you should know real-world uses of alkanes. Anybody drive by a gas station and think about half the way to a gas station is an alkane? Did you think about propane or natural gas, methane? Those are alkanes you use in your daily life. So is Vaseline, baby oil, and half the way to candles are alkanes. Now, there is only one reaction, and also I should have put here, I can't really, because it's done with my software, drawing software, and that is alkanes, and I should also have here cycloalkanes plus oxygen give you CO2, water, and heat. Now, I will just be asking for the products, and heat is not considered a chemical product. It's an important product of this reaction. And you should remember, in my class, you never have to balance equations. Now, next, we started talking about alkenes, double bonds, which you see by 2 lines, and alkynes, 3 lines between 2 carbons. Now, in an alkene, one of those is a pi bond, one is a sigma. And what I don't have here is each bond or each type of bond line and this is something you really should know, that each line is a pair of electrons. So a double bond has 2 pairs of electrons, 2 lines, and a triple bond has 3 pairs of electrons. Now, for our Iupac, alkene, a double bond, you find the longest chain with both carbons of the double bond, name it as an alkane, drop the ane ending, and put in ene. Now, you need a number for if it's acyclic, not in a ring, and also you have to check if it's cis or trans. Cis means the hydrogens are on the same side of the double bond, below or above, and trans, they're opposite. How do you like my hand things? Cis, same, trans, opposite. Now, if it's in a ring, you name, don't forget for rings, use the cyclo along with the large number of carbons, but you change the ane ending to ene, but in a ring, you don't use the number if that's the only functional group present, which in my case, class it will, and you don't use cis or trans. And one of the carbons of the ring double bond is always 1, the other carbon is always 2. Now, for an alkyne, a triple bond, you find the longest chain with both carbons of the triple bond present. You drop the ane ending and you put in, ooh, mistake here, I'm sorry. How did I mess that up? YNE ending, and you need a number. Well, there goes my perfect score. But anyways, triple bond, YNE ending, and a number. There's no cis or trans in alkynes triple bonds. And I don't think I can remember for decades now. Yep, that's how long I've been doing this stuff. I've ever seen a ring with a triple bond in it. All right, now there are reactions you should know. And I've given you the general ones. 1, take a double bond, react with hydrogen and a catalyst. The catalyst can be nickel, platinum, or palladium. You break the pi bond, and each carbon of the double bond gets a hydrogen. Now, important thing. For test number 1, and the rest of the test too, but for test number 1, first of all, there's 4 bonds to carbon. Do you break carbon-carbon single bonds? No. Do you break carbon-carbon single bonds? I'll do this in slow motion. No, don't. Because if you do, you're going to probably get it wrong. Other than combustion, which I just showed you, none of the reactions I show in this class, other than that one, break carbon-carbon single bonds. Pi bonds, yes. Sigma is also known as a single bond, Jimmy. Okay? And again, sigma bond is considered a single bond, and you don't break those. Pi bonds, you break like, ooh, it stopped working. Break like that. But sigma, single bonds, Well, that's a new one. I don't like that. I like, no, that's better. All right, back to our review. All right, if you have a double bond and you react it with halogen gas, X2, X can be fluorine, chlorine, bromine, or iodine. You break the pi bond and one carbon gets X, the other gets also X, the halogen. So they both get a halogen. Now, if you have these first two are symmetrical addition, You add something that's not the same on both sides, HX, or X can be chlorine, bromine, or iodine, to double bond. You break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen in a double bond, and the other carbon gets the halogen. I will never ask you what is Markovnikov's rule, but I expect you to know how to use it. Next, if you take a double bond and add acid catalyst, H plus is how organic chemists show acid catalyst, and water. Think of water as H and OH, H and OH. You break the pi bond. When you add acid and water, one carbon gets the hydrogen, the other gets the hydroxyl group. This also follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets this hydrogen, the other carbon of the double bond gets the hydroxyl group. And as I said in class, I learned it from my professor when I took it as an undergrad, as what I told you, plus he told us, think of it as the rich get richer and the poor get poorer. And we're talking about the hydrogens on the carbon of the double bond, or them that has it gets it. And again, the carbon with the most hydrogens gets the hydrogen from either HX or HOH, and the other gets either the X or the OH. Now, triple bond has two pi bonds, and because organic chemists don't want them balance equations, we're lazy. You have hydrogen and now H2 hydrogen gas, and bracket letters X, letters S, close bracket. That means excess. You have all the hydrogen in the world that hydrogen can react with. And under a catalyst, which is nickel, platinum, or palladium, you break the two pi bonds, and each carbon of the triple bond gets two hydrogens. Now, same thing happens if you use halogen gas, triple bond, two pi bonds. And each time you break a pi bond, each carbon gets a halogen, two pi bonds, each carbon double bond gets two halogens. And again, we use bracket, letter X and S, close bracket, to say you have all the halogen gas in the world, excess, that's what that stands for, to react with anything halogen gas will react with. And here we have fluorine, bromine, chlorine, or iodine. All right, next, and I'll be doing the aromatic problem set today too, we have aromatic compounds. Now, benzene can be drawn any of these three ways. If you draw this, that's not benzene, that's cyclohexane. Be sure to make sure inside the ring, you either put the three double bonds or a circle. And here I did it wrong because I'm so used to not using the circle. I didn't miss that. This is another way you can draw toluene. Benzene, six-membered ring with the three double bonds. Toluene, six-membered ring, three double bonds, and a methyl group. Now, for disubstituted benzene or toluene, and the methyl group counts as one group on toluene, we use the names, not numbers, ortho, meta, and para. If you have something 1,2 disubstituted, it's ortho, 1,3 meta, 1,4 para. Now, I taught you new substituents, and chlorine atom is called a chloro group. Fluorine atom, fluoro. Bromine, bromo. Iodine, iodo, NO2 is called the nitro group. Now, if you have more than two substituents on a benzene ring or toluene, you number, just like you did cyclohexane. Now, important mistakes students make that they shouldn't, or I shouldn't say important. Important thing I should tell you about mistakes students make is for cyclohexane that's substituted, disubstituted. They use ortho, meta, and pair. Nope, 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 nope. You only use ortho, meta, and pair for aromatic compounds, benzene and toluene. How that evolved, I have no idea, but it has. Now, the reactions for benzene, and for this class, because I'm not teaching you directors, all the reactions on test one, also the final, dealing with aromatic compounds, will always start with benzene. Now, the first one is halogenation. Halogen gas, and you need a catalyst, ferric trihalide. And here in real life, this is chlorine or bromine. And you replace one of the hydrogens with a halogen. Why? You don't want to break those bonds, the 3 double bonds, because of the resonance stability. I won't ask you that, but you should know that. And don't forget, when you write the product, if you don't put the double bonds or a circle, that's cyclohexane, and I'll mark it wrong. Oh, I like that, mark it wrong. Don't do that. You'll lose points. Now, if you take a benzene ring, react it with nitric acid, HNO3, sulfuric acid, H2SO4, you put a nitro group, NO2, not NO3, that's a common mistake on test one. A nitro group is NO2 on a benzene ring. If you take sulfur trioxide, SO3, and sulfuric acid, H2SO4, and react it with a benzene ring, you put on a sulfonic acid group. I mentioned it. I didn't ask you to learn that group for nomenclature, but I mentioned it and showed it because we were doing this reaction. And later on, you'll see this is an important reaction that helps companies make the molecule that's the key molecule in your laundry detergent. And finally, we have benzene reacting with alkyl halide. R is an alkyl group, carbons and hydrogens, and X is a halogen. This is called Friedel-Crafts alkylation. You need aluminum trihalide, where X can be chlorine or bromine, and you do something very special. You make a carbon-carbon single bond from the R group to the benzene ring. And the bond from the ring to the R group is to the carbon atom in R that have the halogen in Rx. So this carbon that this benzene ring is attached to is the carbon that had the halogen in this. The end. Any questions? Going once, going twice. All right. Let's continue on with the aromatic problem set. And I've got to show it to you. Hold on. All right, everybody, thumbs up, people. Do you see the aromatic problem set on your screen now? Thank you. All right, let's do it. Now, as I said, one of the major areas on test one is nomenclature. And one type of nomenclature question is, give the Iupac name for the following molecules, 3 points each. By the way, after you take the test number one, you'll understand why I call these practice problems. And the first one, a methyl group on a benzene ring. That's not methylbenzene, it's toluene. Now, we have a toluene, methyl on a benzene ring, and a nitro group. So it's toluene, nitro. It's 1,2 disubstituted, which is ortho. And here we have a benzene ring with an ethyl and an isopropyl. And If you put the isopropyl first and the ethyl second, I'll still give you, that's 1,4 disubstituted, and that would be para. So it's para-ethyl isopropyl benzene. And here we have some more. Now, if you have more than one group, use numbers. And remember, di means 2, tri means 3. And here, you number always in such a way to give the lowest numbers. And that's, since it's not 1, not 2, but 3 bromines on a benzene ring. Bromine is bromo, tri-bromo. When you see di, you need 2 numbers here, tri 3, and you give them the lowest, and it'll be 1, 3, 5. Now, the other type of nomenclature question is draw the condensed structure for the following Iupac names. And the first one is benzene. And don't forget, put the double bonds or a circle, because otherwise that's, guess what, wrong. Now here I made a mistake on the name. I should have had the chloral first, and I corrected it here. And draw para-chloroethylbenzene. Now you have a benzene ring. Now at one point you have chlorine, and you count around 4 times, you have ethyl. Now you could have the switch, you could have the ethyl on the top, chlorine on the bottom. Now meta, I have an unusual way of writing this, meta-bromotoluene. Again, for all organic molecules, I didn't mention it before, you start from the right, move left. Toluene, methyl group with a benzene ring on, or attached to benzene. Meta 1,3 bromo bromine. Now, another way to draw that most of you probably did. Hold on. I closed something I shouldn't have, or I never opened it. All right. Another way, which probably most of you drew it, meta bromotoluene, toluene, benzene ring with a methyl group. Don't forget the bonds inside. And then meta is 1, 2, 3 disubstituted. And this is the way most of you drew. Mine was just rotated 180 degrees along the axis of carbon 2 and 5. Ooh, that's pretty heady. And here I forgot the di, sorry. 1-ethyl 2,3 di and propylbenzene. Start from the right, move left, benzene ring. I have on carbon 2 and 3 and propyl, and carbon 1 ethyl. All right, let's move to some of the reactions. And if we look at A, halogenation, and A and B are the only reactions I can ask on test 1. And here they are. When you have a halogen plus ferric trihalide, either bromine or chlorine, you replace the hydrogen with a halogen. Remember, this is a substitution reaction. You never, almost never break the double bonds in a benzene ring. Now, here we have, what's different? A benzene ring, methyl chloride, a chlorine on a R group, and that's Friedel-Crafts alkylation. And here's the general reaction, benzene, alkyl halide, aluminum trihalide, and you make a bond to the carbon with the halogen. Do you break carbon-carbon single bonds? No, but this only has 1 carbon, so you make toluene. Probably the most expensive way to make toluene. Here we have an ethyl group, same reaction, and got fancy on you. Here we have benzene ring. My R group is the cyclopentane ring with the chlorine, and you make this interesting molecule. Now, if you take a benzene ring and react it with sulfur trioxide and sulfuric acid, SO3, H2SO4, you put on there a sulfonic acid group. And finally, and this is the only reaction I can ask you for this reaction because I'm not doing directors, having something on the benzene ring already. And the last one, this is the only one I can ask you on a test, hint, is benzene ring plus HNO3, nitric acid, H2SO4, sulfuric acid. And you put on an NO2 group. Even though here it has HNO3, the group you put on is NO2. Be careful, don't write a 3 there. If you do, that's wrong. It's NO2. And that is the review and the problem set for aromatic. You people are good to go for Thursday. You have all the rest of the day to study. You had yesterday too. And that's a week and a half time almost that it would be. And I always try and the fall, winter, finish up a week before our test, the material that will be on the test. And the summer it's compressed. So a couple of days is 1 week. I keep to my promise to myself. Any questions? Excuse me. All right, let's get back to alcohols. Remember, alcohols will not be on test number 1, but will be on test number 2. And it happens in the summer, actually fall, winter. I get ahead like this, and that's because I don't like doing stuff till last minute that will be on a test. I know how to schedule. All right, let me open up that file. All right, yesterday, everybody see common names on your screen? Thumbs up, people. Thank you. All right, yesterday I went through the common names, and you should know when it comes to common name, how to draw the structure. On a common name, I'll never ask, here's the structure, give the common name, but I will ask on a test, here's the common name, give the structure. And I went through this yesterday. So let's move on. Now, I talked about phenol already. Phenol, some people call it phenol, I don't, is a benzene ring with a hydroxyl group. And derivatives are named similar to toluene, except instead of toluene with a methyl group, you have phenol with the hydroxyl. All right. I'm going to turn the switch. Will this be on a test? To the click, to the off position, click. And that means this won't be on a test or final, but it's good background information you should know about alcohols because it'll help you understand other things I will talk about, which is why I go through it. Now, alcohols can hydrogen bond. Well, what's a hydrogen bond, in case you forgot? It's a weak intermolecular. Intermolecular means, hold on. Keep on, today is forget to share screen button day. All right, now you can see it. Let's talk about hydrogen bonding of alcohols. What is a hydrogen bond? Well, it's a weak intermolecular attraction, not a real bond, but it's still a weak force that's very important between non-bonding electrons on a nitrogen, oxygen, or fluorine, and with the hydrogen atom bonded to that type of atom, nitrogen, oxygen, fluorine, in another molecule. Now, this won't be on a test ever, but they're weaker than single bonds, but have their strength has a significant effect on key physical properties, such as boiling point and solubility, and I'll teach you later, in certain polar solvents like water. And alcohols can hydrogen bond with each other and water. Now, interesting thing, when we talk about hydrogen bonding, water can hydrogen bond to itself, and that raises the boiling point of water. And it does that for alcohols too, and their melting points. What that means is if it wasn't for hydrogen bonding, this water in this bottle wouldn't be a liquid at this temperature, it would be a gas. And think about it, on our planet, if all the water on our planet was a gas at room temperature, like right now, my house is not quite comfortable. Plus, you can't see it. No, you can't. I got a little fan behind me too. Because my bigger fan puts light shadows, and it's not good for students watching me on Zoom. So that's why I don't use my ceiling fan. But also my hair goes whoop, 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 whoop. It distracts students too. But if everything was a gas, including the water in your blood, we wouldn't exist the way we do now on this planet. That's due to hydrogen bonding. And alcohols, because of hydrogen bonding, the smaller molecular weight alcohols are water soluble. And I should mention, bartenders don't like to be told, know why the alcohol in the drink you're giving me is able to dissolve in the water, like if they have it in pop or whatever, because of hydrogen bonding. They do not like to hear that. Now, the next slide, again, the switch is in, click the off position, but it's still important to know the acidity of alcohols and phenols. Alcohols are very, very weak acids. Remember, an acid under the Bronsted theory of acids and bases, which I'll never ask on a test, or final, is something that's a proton H plus donor. And turns out alcohols are really, really, really weak acids, but their conjugate bases are strong bases. I'll show you this in a second. Now, phenol is a weak acid, but it's much stronger than that and the regular alcohols, and that's due to what we call resonance stabilization of the phenoxide ion. By the way, my last patent, I used the phenoxide ion in such a way nobody else had ever done. Ooh, see board, I've got to get to work. Here's a general alcohol, and as a base, acid base going from left to right, this would be an acid. Proton donor. It hardly goes that way. That's why I have a little arrow there. It stays mostly here, why I have a big arrow there. But what that means is this is called the alkoxide. Ion or anion. And if this is a very weak acid, alkoxide is a very, very strong base. And it's stronger than sodium hydroxide and potassium hydroxide. Now, it turns out phenol is a stronger acid, which is why I'm drawing the arrows like that. It's time for Dr. White to have some fun, and I will. And you can draw resonance structures. The resonance structure is where you just move electrons around. And you show that by arrows. And if I move the electrons there and form a bond, these will go here. And double-headed arrows are resonance. And this is a resonance form. Now I can draw two more. I won't because I'm not going to put this on test. But whenever you can draw resonance forms of a molecular species, it makes it more stable. And by making it more stable, that equilibrium will go more to the right, meaning it's a stronger acid. And another chapter will encounter the same type of concept. When you can draw resonance structures of something, it makes what you're going to more stable. Again, switches off. Now, alcohols can also, switches off, click on this slide. Alcohols can also function as weak bases. A base is a proton acceptor, and they can be protonated. That's what we mean by accept a proton. And I don't know if I've taught this to you. The letters in that sentence, I.E, is Latin, and I don't know the exact Latin words for that is, they react with strong acids. And I don't know why there's an extra comma here. There shouldn't be. And this is the first step in two important reactions of alcohols I will teach you. And let me show you that on the board. Again, this is switches off. It forms this, and everybody, if you look at what I just formed right here, what do you see? Two hydrogens and oxygen. Two hydrogens and oxygen. H2, two hydrogens, oxygen, oh, H2O, water. And this leaves, and we'll learn later on, the important reaction, this first step where you add an acid, and you lose water, and you form a very reactive species called the carbonium ion. And these carbonium ions are really, really reactive, but this won't be on its test. All right. In coming chapters, I'll go through nomenclature, which I did for alcohols, some interesting features, which I just did, and then how do you make them? That's the fun part. And how do you react them? Now, this is the only reaction that will be on two tests. Stuff I talk about in test one, material isn't going to be on test two. But this is going to be on both. Why? Because this deals with alcohols. If you take a double bond reacting with acid and water, you break the pi bond, one carbon gets H, the other gets OH, and it follows Markov-Zayces rule. So this is a synthesis. Remember, synthesis is a fancy word for to make. And this is one way to make alcohols. Since we've already done this reaction, I'll just do one. Better yet, have you do one. Reaction. And why don't you try this? And I'll help you out. Hopefully you know this by now. And there you go. What's the organic product or products that are following? Nope, somebody's not done yet, so I'll end the poll and we'll wait a little while. I jumped the gun. All right, I think everybody's done, and I better finish up so we can start our break. And what do we have that's different? Look at a molecule. I forgot to mention in review, when you look at a molecule, look for what's different, what's not a carbon-carbon single bond, carbon or hydrogen atom, should get your attention like that. And we have a double bond reacting with acid and water. Remember, water is HOH, break the pi bond, one carbon gets H, the other gets OH, follows Markov-Nikolsky rule. The carbon with the most hydrogens, double bond. This has two hydrogens, this has one. Hopefully all pick two is greater than one. Do you break carbon-carbon single bonds? No. Here I have my two carbons with double bond. They become these two. The N carbon has the most hydrogen, so gets this. The other one gets the OH. You know, there are 4 bonds to carbon, so I can put in my hydrogens. And that's how you do it. And if I look at, oh, we went over 2 minutes. Come back at 2:57. Hopefully you know how to read a watch, or you have a times piece. Not go to time.is on the internet, you can see the time, and I'll see you at 2:57. I can get up and stretch. See you in 5. Let's try that again with my mic on. Time to get going. All right, we're talking about alcohols, and I just showed you the synthesis. Since we've done that before, I'm not going to do any more examples because we did that for the alkenes, alkynes. So let's move on. Now, let's talk about reactions of alcohols. And let me show you it. And on the screen is called dehydration of alcohol to alkenes, or just dehydration of alcohols. And what is dehydration? You lose water. If you look over here, if I lose the H here and a hydroxyl group OH on adjacent next door carbon, you lose water, and between those two carbons, you form a double bond. Now, how do you do this? You react it with sulfuric acid, H2SO4, and this little triangle is heat. And I also, not always, but today I did, but on tests I don't have to, I have the temperature. This tells you it's pretty high heat. So you do this. Now, there's important. This reaction follows Zayces Rule, and Zayces Rule is developed by Dr. Zaitsev, another famous Russian organic chemist. And the rule, and you don't have to write this down, is the major product in the intramolecular alcohol dehydration reaction is the alkene that has a greater number of alkyl groups attached to the carbon atoms, double bond. You look at that and you go, what? What? Let's look. Now, before I do, everybody take a deep breath, let it out, take a deep breath, let it out, take one more, let's do 3. Let it out. Are you nice and relaxed? Good. Of all the reactions this semester, this is the one of the most challenging. Relax, and it takes some practice to get it, wrap your hands around it. Now, what I'm going to do now, unlike what I normally do, I'm only going to do one example because this takes a while for you to look at and figure out what's going on. But I'll do one example. But when we do the practice problems, I'll go through some more so you can get a hang of it. But, and maybe maybe tomorrow or maybe Monday would be better. I'll come back and do another example. That'll give you time because tomorrow you'll probably be still studying for test number 1. But over the weekend, hopefully, you're working on the alcohols problem set because we should finish by tomorrow. So let's look at dehydration of alcohols in Zayces Rule. All right, if we look at the reaction right here, we react this molecule with sulfuric acid. And let me make a better triangle. That looks awful. And in a whiteboard in a school, I'd probably be doing the same thing, but with an eraser in my hand. All right, now let's look at the general reaction. Here we have 2 carbons. And they're adjacent next to each other. One has a hydrogen, the other has hydroxyl. And you lose water, H2O, and form a double bond between those 2 carbons. Now, if we look here at this molecule, here's the carbon with the hydroxyl group. But on this side and this side, we have adjacent carbons, hydrogens on carbons. Now, if I lose the hydroxyl group and a hydrogen from carbon A, this is the product I'll get. Let me do this first. You don't break carbon-carbon single bonds, and between A and this carbon, I'll form a double bond. And I know there are 4 bonds to carbon, so I can put in my hydrogens. Now, if we lose the hydroxyl group here and a hydrogen from B, I'll get this product. Now, what is Zayces Rule? Zayces Rule, the way I will teach you, is the product you get is the molecule that has, and listen carefully, the most carbon atoms directly bonded to the double bond carbons. Again, the most carbon atoms directly bonded to the carbons of the double bond. And if we look at A, this is the only carbon, 1. We look at B, we don't count this carbon because it's not directly bonded a carbon atom to the carbons in double bond. But in B, we have this and this, 2. So which is higher, 2 carbons or 1? And hopefully all pick 2. And therefore, for the way I teach it, you'll get B as your answer, not A. Now, in real life, what happens is you get about 90% B and a small, like 10% A. B is the major product, A is the minor. But to make your life easier, don't tell anybody I'm being nice. I teach Zayces Rule. The one with the most carbons is what you get. In this case, B. All right, let me go through it again. Here we have an alcohol. And on adjacent carbons, A and B, we have a hydrogen because we're doing this reaction. If I lose the hydroxyl group and a hydrogen from A, this is what I'll make because the double bond is between these 2 carbons. Now, if I lose the hydroxyl group and now from hydrogen from B, I'll form this double bond. And Zayces Rule is the molecule, the alkene double bond that you get is the one that has the most carbon atoms, this is important, directly bonded to the carbons of the double bond. In this case, this carbon, this double bond only has this carbon atom. This, you don't count this one. This one has 2, which is the larger number. Hopefully I'll pick 2 over 1, and therefore this is the answer. And that's how you do Zayces Rule. And like I said, this is a really complex reaction, much more than Markovnikov's rule. And therefore, I'm not going to do another example, but on Monday, I'll do one and then let you have some fun, because I think most of you are probably going to be working on getting ready for test number 1 tomorrow. All right, let's move on. Like I said, this is probably one of the most challenging reactions of this semester. Oh, good news. Let's do a simple one. This is a fun reaction. Now, the reaction is if you take an alcohol, ooh, look, I went Technicolor, react it with an acid HX, where I don't have here, so instant X can be chlorine, bromine, or iodine. And what happens is you replace the hydroxyl group with the halogen on the carbon that had the hydroxyl group. And you make water. Now you'll see some of the slides, I'll do this because one semester I had these two twins. Yes, I've had over the years, I think I've had 1, 2, 3, or no, 4 sets of twins in my class. 3 of the times they were both in at the same time. One time they were a year apart. And I remember coming to the class when the second one was there. I'm looking at her and saying, after class, can I see you? Say, you look familiar. Were you in my class before? Another class? She said, no, you had my sister, twin sister, a year ago. And they were twins. They even wore the same style, color, and type of glasses. I mean, all my twins I've had have been identical. But one year I had these two twins and both of them got upset. I mean, really did. If I didn't put the inorganic stuff, which normally I just ignore. So I started putting them on some of the slides to keep them happy. You don't want upset twins. It's not fun. But anyways, let's do this. Now, sometimes I'll put the HCl, like in this case, over the arrow. Here, I put it before. So look at a molecule. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Should get your attention like that. And if you, oxygen with a hydrogen and a carbon, alcohol. And HCl is HX. Remember, X can be chlorine, bromine, or iodine. And you replace the hydroxyl group with the halogen on the carbon that had the hydroxyl group. And that's this carbon. Do you break carbon-carbon single bonds? No. So I start with 4. I better end up with 4. Which carbon had the hydroxyl group? This one. It will have the halogen, which in this case is chlorine. And halogen counts as 1 bond, so 4 bonds to carbon. And that's how you do it. And now it's your turn. And like I said, sometimes I'll put it on top of the arrow or put it plus. And the question is, give the organic product or products for a following reaction. Your turn. And with the people we have today, I can do the following. Hopefully all have it working. When you're done, give me a thumbs up. Or thank you, yeah, or a heart. I love it. Thank you. And thank you, Jimmy. And we'll wait for the other two to finish. Quick reminder, if you didn't do it yesterday, don't forget the hand in the lab, distillation lab that was due yesterday. Again, if you didn't hand in the lab yesterday, make sure you hand it in. As they say, ASAP, as soon as possible. All right, well, I'm going to guess I'll give everybody a little more time. All right, let's do this. And the question is, what's the product or product for the following reaction? So if I look up here, what's different? What's that carbon? What's that? Ooh, oxygen with a hydrogen and a carbon. That's an alcohol. I'm reacting it with this HCBr, which is HX, an acid, hydrogen halogen acid, where X can be chlorine, bromine, or iodine. And what do? Replace the hydroxyl group with a halogen on the carbon that the hydroxyl group was on. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, and a methyl group makes 5. So I'm going to have 1, 2, 3, 4, and my methyl group makes 5. Which carbon has the hydroxyl group? This one. Which is this one? Which will get the halogen. In this case, it's bromine. And you can have it pointed down too. And now I remember there's 4 bonds to carbon. And I can put in my hydrogens. And that's how you do it. Now, on test 1, I'll have 1 synthesis problem. You know something? After next break, we'll do a practice or 2 of synthesis. 1 practice for you, because I didn't do that many. But I'm going to do one now for the alcohols, because on test number 2, even though it's cruel and unusual punishment to do a lot of those, which is still outlawed by the Supreme Court of the United States, on test number 2, I usually have either 3 or 4 synthesis, usually 3, but I might put 4. And you should know how to do that, because that's the fun part of organic chemistry. But I'm biased because I'm a synthetic organic chemist. Remember, synthesis means to make. What would you react with HI to make that molecule? And hint, I'm going to let you try it on your own, then I'll show you how it's done. As they say, I think I'm getting my sea legs back because summer is pretty grueling teaching, because you're spending a lot of time in a short part of time. And on Monday was the first time where I taught a very long class at College of DuPage and came back here and taught a long class. And if you look at the videotape, you'll see where I just about, like I did for 30 seconds, not off because I was so burnt out. But now that I got my sea legs, yes, I taught today, but Dr. White's all fired up and like the Energizer Bunny, boom, boom, boom. I'm going to keep on going. Should I cut that out of the video? No. By the way, tomorrow's lab, don't forget to bring your nose. If we were face to face, I'd be telling you that. For tomorrow's lab, don't forget to bring your nose. And I should have pointed out in the previous problem, that's the R group. And like I said, these are a little more challenging, but they're the fun part. All right, let's do this. So how do you do this? How do you find what do you react with HI, hydrogen iodide, to make this molecule? Well, you look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, which gets your attention like, you know what's going to happen, like that. And if we look at, ooh, an iodine on a carbon here, and the rest of this is this carbons and hydrogens. And that's in our group. And how do we show the halogens X? And what do we have here? HX. And remember, X can be chlorine, bromine, or iodine. And what do we react with HX to replace something with a halogen? And the answer is an alcohol. And what's my R group? This. If this is what I end up with, I have to start with this, the ring with the methyl group. Think about it. 5 weeks ago, would you know what I meant when I said a ring with a methyl group, CH3? No. See how much you've learned? Now, the carbon with the halogen will be the carbon you started with the alcohol, which is this carbon. So that's that. And if you take this molecule, react it with HI, you'll make this molecule. And that's how synthesis works. You're working backwards. But that's how you figure out how you make molecules, that we use in our everyday life. Now, let's move on. Now, the next reaction is the reaction of alcohols with thionyl chloride. Thionyl chloride, which I'll never ask you on a test what it is SOCl2. SOCl2 is thionyl chloride. And what happens when you react an alcohol with thionyl chloride, you replace the hydroxyl group with a chlorine. And you make some inorganic stuff, which you don't have to worry about. But like I said, that was to keep those twins happy. Oh, they sometimes could be, how should I say, challenging to deal with, but they were very outstanding students. So I tried to keep them happy. All right, now why would we do something like that considering the last reaction? Well, let me show you something. The following you do not have to copy down. But let's say we have this molecule. And we wanted to replace this hydroxyl group with a chlorine, but keep the double bond. So you say, all right, I'll take this, react it with HCl. Remember, ROH plus HX, where X equals chlorine, bromine, or iodine. You replace the hydroxyl group with X. And you say, okay, I can do that. And you get this product. And there you go. But that's not the whole story. This is not the only thing you get. You say, why? Well, we've got a double bond. And you learn that a double bond reacts with HX, X is still chlorine, bromine, iodine. You break the pi bond, one carbon gets H, the other gets X. So this double bond could react, and you could get where that reacts alone. Oops. Remember, carbon with the most hydrogens gets the hydrogen, Markov-Nikov's rule, break the pi bond, the other carbon gets the chlorine. And if the alcohol didn't react, you'd get this. If both the alcohol and double bond react, you would get also this. That should be a 2. And notice I have 3 products. If I can spell it right. And I'd get a big mess. I could get a couple of, I don't know which one would be the major product, but there's the possibility of getting all 3. And that's not what I want. I want this only. So it turns out, and I don't know which chemist did, came up with the reaction of thionyl chloride. And thionyl chloride doesn't react with double bonds. It only reacts with alcohols. Therefore, if I did the one above, I'd get what I want, but I won't ever give you reactions until we get later into carbohydrates with more than one functional group in a molecule. So let's do the following. If we look at the following, if we react this with thionyl chloride, SOCl2, what happens? Well, what's different here? Alcohol. We're reacting with thionyl chloride, and it replaces the hydroxyl group on the carbon that had the hydroxyl group with a chlorine. So what's my R group? And therefore, do I break carbon-carbon single bonds? No. And here's my carbon with my alcohol, this one, and general reaction, replace it with a chlorine. And I did. And now it's time for you to have some fun. And why don't you do that? What would be the organic product or products are the following? Let me clean this up real quick. There we go. Looked like a double bond. It was just an excess line. And your turn. Well, if you haven't registered to vote, don't forget to register to vote in Illinois. The primary that's coming up, I think it's the 25th. I just got yesterday my mail-in ballot because since the pandemic, I find it's more easier. And probably after the pandemic, I'll continue to get a mail-in ballot and just make sure I get it in time to be counted. Anybody else done? All right, I think I better get to work. All right, if we look at this molecule, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? If I look, ooh, oxygen with a hydrogen and a carbon, that's an alcohol. What am I reacting it with? Thionyl chloride, SOCl2. And what do? Replace the hydroxyl group on the carbon in the R group with a chlorine. And what's my R group? Well, all of that. Do you break carbon-carbon single bonds? No. I have 1, 2, 3, 4, 5 carbons across. 5 carbons across. Right here and right here, I have a methyl group. And this carbon has the hydroxyl group, which is this carbon, will get the chlorine. And now I know there are 4 bonds to carbon, so I can do the high-level math to put in the hydrogens. And there you go. Oh, let's have fun and do a synthesis problem. What do you react with thionyl chloride, SOCl2, to make this molecule? Your turn. What do I react this right here, something with this, to make this compound? Oh, I didn't look at my chat. Thank you, Nana. Bad, Dr. White. This should be CH3. Thank you very much. And once in a while, even I make mistakes, which is why a while back I said, it's your obligation to let me know if I make a mistake, and I did. Oh. Bad, Dr. White. Keep an eye on me. I made one mistake. I might make another. excuse me. All right, let's do this. Now, how do you do this? How do you find out? What do you react? That's why I have this question mark here with SOCl2 to make this molecule right here. Well, let's look for what's different. What's not carbon? What's not hydrogen? Ooh, a halogen on a carbon. Chlorine, RX. Well, actually better, I should. Not just a halogen. Let's make it a chlorine. Why did I do that? Because I have the thionyl chloride. And what do you react with thionyl chloride to put a halogen, a chlorine actually, on our group? And the answer is an alcohol. So what's my R group? All these carbons. 1, 2, 3, 4, 5. If I end up with 5, I better start with 5. 1, 2, 3, 4, 5. Next, on one of the carbons, I have a chlorine. It's the N carbon. And this reaction, the carbon that had the hydroxyl will be the carbon that has the chlorine. The carbon that had the hydroxyl group OH on it will be the carbon with the chlorine. So if this carbon has the chlorine, this carbon, this end one, has to have the hydroxyl group. I know there are 4, yes, 4 bonds to carbon, so I can put in my hydrogens. And that's the answer. Again, I have a chlorine on a carbon, alkyl chloride, and I know thionyl chloride, SOCl2, reacts with an alcohol to put a chlorine, replace the hydroxyl group with a chlorine. And the carbon that had the chlorine is the carbon that had the hydroxyl group. Now, I haven't done it for a day or so, but one of the questions you should be asking yourself always is, why am I learning this stuff? Well, the obvious answer is you want to get a good grade in this class because someone told you had to take organic to get into a school or a program at a school. And so that's why you're taking it. But why really should we look at? Let's look at the following. Now, in our country and the world, we have artificial sweeteners. And one of the more popular ones is called Splenda. And Splenda is a product that when you taste it in something, your tongue tells your brain, ooh, that's sweet, but it doesn't have any calories to it. Now, the key ingredient that makes your tongue tell your brain, ooh, that's sweet, is a compound called sucralose. And sucralose has this structure. Does everybody see that on the screen right now? Chlorines and everything, and rings. Thank you, Jimmy. Now, if we look right here on this ring, you have a chlorine. On this bend, you have a carbon, you have a chlorine. And this bend right here, you have a chlorine. And this molecule has 3 chlorines. And they make it, and it's not that expensive because sucralose isn't like $1,000 for a box of a couple hundred. It's reasonably priced and is usable as a sweetener, artificial sweeteners. Now, the question was, why learn the reactions I just showed you? And sucralose I'll talk about that, Nana, after our break. And sucralose gets its name. Everybody see on the screen a molecule with a lot of OH groups? This is called sucrose, otherwise known as table sugar. And 3 of the hydroxyl groups in sucrose are changed to chlorines. One of these right here, this one, and I think this one. Well, how do they do that? How do they change these hydroxyl groups to these chlorines? Well, the answer is by one of the 2 reactions I just showed you. Which one? They don't tell. This is a trade secret. So that's why we're learning these reactions. Now, Nana brought a good point about, does this cause cancer or not? And after our break, because it's time for our break now, I'll talk about my own personal opinion, what I feel about it as an organic chemist and someone who's been trained to use my brain, and I have. With that, let's take a 5-minute break. I'll see you at 3:50. And go get up and stretch a little. time to get going. Now, before the break, Nana asked me about, do those cause cancer? The good question is, I don't know. I've looked and I've seen where people feel there's not enough evidence that that does. They really feel a number of people, I'm just saying some, or some of the evidence just doesn't show it. But however, for me personally, molecules that are small, that have halogens in them, can be carcinogenic, cause cancer. That's why when I use artificial sweetener, I never use Splenda. My sister did, and I told her, you know, I wouldn't if I were you, and she never got cancer, but I just wouldn't. Now, I used for a long time Equal, which I'll teach you later, is a modified amino acids compound. And it did the same thing, it makes it taste sweet, but it's no calories. Now, a number of years ago, it's been about 6 or 7, on my own, doing it to myself, because it's something I made and kept too long in my refrigerator, I gave myself food poisoning. I got pretty sick. Oh, I get sick. And I went to my doctor, who was great, and he gave here's what you do and all that. And I just read this article in the New York Times, I think it was. And I asked him, are artificial sweeteners good for you or give you problems? Because I read this article. He said, no, I don't know. They affect me in a negative way, meaning the doctor. And up then I've been drinking all my pop with Equal in it as artificial sweeteners, in my tea, which I drink a lot. I had a cup earlier today, and no, it didn't have an artificial sweetener. And what was that? Jimmy, I'll get back to you in a second. What was that article? And the article didn't deal with cancer, but it got my attention because it dealt with something just as important. And that was 2 doctors in New York who were gastrointestinal doctors. That was their specialty. And they happened to be overweight, were wondering, did artificial sweeteners affect things in your stomach? In other words, the flora, the microbiotics, or whatever it's called, I think I'm saying it wrong, but the flora in your stomach or the biotics, what's the right term? If anybody knows, let me know, put it in the chat, thank you, Jimmy, microbiotic or biotic. But anyways, that affect that. So they, with about 10 of their friends, they consumed stuff with tea, drinks or something with artificial sweeteners. They did both Equal and Splenda. And then by your poop, they analyzed it for what's in there, which can tells you what's the flora bionic, or I'm going to have to look that up. But anyways, after class and tell you tomorrow. But what happens to it? And what they found was having artificial sweeteners, when you consume it, kills about 80% of that in your gut, which is not good if you're trying to lose weight. And they found out in a day or two, you can build it back up if you don't have artificial sweeteners, but it does that kind of damage, not permanent, like gonna kill you damage, but that affects your hunger, makes you more hungry later on. And that's the opposite of what you're trying to do, losing weight. So when I read that and talked to my doctor, plus with being sick like that with food poisoning, I cut out all artificial sweeteners. And I went back to sugar, sucrose. And in fact, I had a couple of cases of pop with artificial sweetener. And one of the colleges I went to, I brought it in and donated it to, I think the woman I knew at that time who was helped run the dentist program training for dental assistants. I said, here, give this away, and it did. So that's just my personal opinion. One, I don't do artificial sweeteners because what it does to your stomach, negative way, in terms of killing off the flora or whatever in there. Now, in terms of Jimmy's question, organic versus synthetic nutrients, I'm not sure which nutrients you're talking about. Now, if you're talking about fertilizer made from ammonia, guess what? They've been getting ammonia for years from animal and human waste before they had artificial fertilizers. And honestly, I haven't even looked into it, so I don't know the pros and cons. So in that case, I just don't know. Okay. All right, let's continue on with the, oh, I almost forgot one more thing while you got me on a roll. This won't be on a test or anything, same thing with the Splenda equal. Now, when you run a reaction where you put a hydroxyl group is very important because it can have very serious effects. If you put it on this carbon or this carbon, where things are in a molecule are very important. And let's go, let me take you to the internet. Everybody see Benzene on your screen and some colorful stuff on the right? Thumbs up, people. All right, thank you, Jimmy. Now, in the United States, a number of years ago, 2007, wow, it's that long ago, there was an Australian company that made a great product, and in the United States, they were called Aquadots. In parts of Australia, they were called Benzies, and they had other names. And turned out some children were getting very sick. Well, look at this product. What was the product? You had these little dots, you put them in a tray, you sprayed them with water, and they stuck together. And you could take it out, they don't show it here, and make all sorts of interesting designs like that you could keep. Well, if you look at the product, it's got these little beads that are colorful. And guess what? Little kids who this is designed for, oh, is this candy? And they pop it in their mouth and swallow it. Well, it turns out when the company started selling this, they had tested that and it was harmless. Yeah, it's going to come out colorful at the end, but it's going to be somewhat harmless. Well, it turned out and they say how a couple of children through the country became very sick, and some in the United States. And what was the problem? Well, when this became very popular, the company in Australia does what companies do, and I work for companies that do it for chemicals. You farm it out to have someone else make it to help you make more of that popular stuff. And that's called toll producing. I don't know where it got its name, toll producing. Well, when you have someone else help make that, well, they had it toll produced in China. And the Chinese company said, ooh, if we substitute one of the chemicals this company told us to use with something else that's cheaper, we can make more money. And they did. And what did they substitute? A plasticizer. And the plasticizer they substituted, the original compound should have been 1,5-pentane diol. And they substituted with cheaper 1,4-butane diol. And I should have mentioned one carbon made a difference. Oh, you did, Jimmy? Did you like it? I always thought it was a neat product. I never played with it, but just the chemistry. All right, let's go to my whiteboard. Again, this won't be on a test, but shows you one carbon can make a difference. This is called 1,4-pentane. And it's got not one, but two alcohols, 1, 2, 3, 4. Diol, di-2-OL tells you alcohol. It's never be on my test. Now, this is also 1, 2, 3, 4, 1, 4, but has one less carbon, butane diol. And this is a lot cheaper than this. And the Chinese company started using that. What's wrong with this compound right here? Well, it turns out in your body, I think it's your liver, but don't quote me on that. Your body oxidizes that to another compound. And it's called GBH, and I'll talk about it later on. And well, I'll have to ask you about that, Jimmy, later on. But anyways, that compound it is oxidized to is known also today as the date rape drug, which in a little trial can cause serious harm, medical problems. And they've pulled the product. I think they've since reintroduced it, but you don't hear much about it. All right, I thought I'd share you that story, which is somewhat sad but interesting, that you have to watch out what you're making and what you're substituting. All right, let's move on. Now, before I move on to this part, I'm going to talk about something that I'm going to turn the switch. Will this be on a test to the off position? But it's background information you should know about. And that's the types of alcohols. This will never be on a test, but I'll use the terminology. Now, something I'm going to introduce, which I haven't talked about before, is R prime. And I'll explain it in a second, and R double prime. Now, right here, we have what's called a primary alcohol. Which is abbreviated 1 with the degree sign, ROH. And you know what an R group is, something with carbons and hydrogens. Now here we have, and primary means there's one R group on the carbon with the hydroxyl group, the alcohol. This has two R groups, and it's called the secondary alcohol. And it's abbreviated by 2 degree sign ROH. Now, what is the R prime? Just like in math, you have X and Y are different variables. R and R prime tells you these can be the same or different amount of carbons or structures, carbon and hydrogens. Now here we have, and secondary means there's two R groups, same or different, on the carbon of an alcohol with the R groups, and it's a secondary. Now in this one here, we have 1, 2, 3. And like you have R prime, and R double prime, is this the same as math, as you say X, Y, and Z? They can be the same or different. So you have R with 5 carbons, R prime 10, R double prime 2, or they can all be the same, just like X, Y, and Z could be the same number. And this is called a tertiary alcohol. It's got 3 R groups on the carbon with the hydroxyl. And there you have a tertiary alcohol. So 1 R group on the carbon with the hydroxyl group is a primary alcohol, 2 R groups is a secondary alcohol, and 3 R groups is a tertiary alcohol. And I'll never ask that on a test, but I'll use that terminology. So let's go back to our slide. Next reaction I want to talk about is oxidation of alcohols. And there are 2 reactions I'm going to talk about. Now, instead of teaching you all the oxidation reaction or reagents like KMNO4, Na2CO3O7, and others, I'm going to use what organic chemists use, O bracket, O close bracket. That means oxidation reagent. And here, if you take a primary alcohol, oxidize it, you get an aldehyde. Now, my software doesn't put the carbon in there. There should be a carbon in there. So I'm going to write this on my whiteboard like it should be help you out. If you take a primary alcohol and you oxidize it, you lose a hydrogen here and hydrogen here, and you form a carbon-oxygen double bond. And this is called, and we'll learn later in 2 chapters, I believe, an aldehyde. And I better warn you, Mother Nature, and especially Dr. White, loves aldehydes. My first US patent dealt with aldehydes, so I like them. And that's what you get. Now, another way of writing an aldehyde, which I like this way myself personally, is like this. And these are the same. So whenever you take a primary alcohol and oxidize it, you'll get an aldehyde. So let's try this. And the question is, what's the product or products? Remember, all these reactions, just like I just showed you, for use to make molecules like to make Splenda, are building blocks, organic tools, organic chemists use to make things. And I've done these reactions with oxidation of alcohols to make aldehydes because I did research in aldehydes. I did also for my PhD thesis, I had to do this reaction. Now, what do we have here? A primary alcohol. What's this? An oxidizing reagent. If you take a primary alcohol and you oxidize it, this carbon with the hydroxyl group will be this carbon double bond to oxygen. Since there's 4 bonds to carbon, I need a hydrogen there. So what's my R group? These carbons. This is the carbon with the hydroxyl group. Do you break carbon-carbon single bonds? No. So I have 2 carbons. Then this carbon right here will be double bond to oxygen with a hydrogen. And I know there are 4 bonds to carbon. And that's an aldehyde you just made. Oh, by the way, how many like the smell and taste of cherries or almonds? Well, an aldehyde is responsible for that, and I'll teach you in a couple of chapters which one. All right, your turn. What would be the product or products, organic product or products of the following reaction? And don't forget to vote. In this case, on my poll. All right, time for me to get the word. And the question is, what's the product or products for this reaction? And if we look at this molecule, what's different? What's not a carbon? What's not? Ooh, hydrogen, oxygen right there with a hydrogen and a carbon. That's a primary alcohol. If I oxidize it, that's what O in the brackets means. I lose this hydrogen one here, form a carbon oxygen double bond, and that carbon still has a hydrogen and aldehyde. So what's my R group? This right here. Another way of thinking is I start with 1, 2, 3, 4, 5 carbons. I better end up with 5 carbons. 1, 2, 3, 4, 5. The carbon with the hydroxyl group will now be double bond to oxygen with a hydrogen, 4 bonds to that carbon now, and the rest I can put my 4 bonds to. And there we go. We made a aldehyde, and Dr. White is very happy. I love aldehydes. Now, as I mentioned, on test number 2, there'll be a couple, usually about 3 or 4, probably 3 synthesis problems. So let's try one. I'm going to let you try one, and then I'll do it. What would I oxidize, react with oxidation reagent to make that molecule? Your turn. Remember, what I'm going over now will be on test 2, not test number 1. Looking over here, that's where my clock is. So I know when to put out a poll. Because none of you have your webcams on, so I can't see if you're done. If you're done early, please be patient. I try and give everybody enough time to finish. All right, I think it's time for me to get to work. And the question is, what's the starting material? What do you react by oxidation to make this compound? And you look for what's different. What's not carbon, what's not hydrogen, get your attention like that. Or carbon-carbon single bond. Oh, we've got an oxygen there. And notice it's double bond to carbon with hydrogens. Then it's got carbons here, R, and that's an aldehyde. And what do you oxidize? Remember, this means oxidation, reagent, oxidize to do that. And the answer is a primary alcohol. And the carbon double bond to oxygen is the carbon that had the hydroxyl group. Now, do you break carbon-carbon single bonds? No. So notice here we have 1, 2, 3, 4 carbons. We better start with 4 carbons. I can also say what's attached to the carbon double bond to oxygen is my R group. So that's my R group. Then I'll have this carbon, which will have the hydroxyl group. I know there are 4 bonds to carbon. And there we go. And that's how you do it. All right. Now, something I forgot to do earlier, and we'll take a break from alcohols. That doesn't sound right. Anyways, we'll stop for a second, do something else, which will help you tomorrow. And that is, let's look at the following reactions. I went through this yesterday, but I should do another example. And that is the following. And if we look at this reaction, the question is, what's the product or products for the following reaction? Well, first of all, let's look at the smog. I'll tell you what, I'm going to do something interesting. I think you try that. What would be the product or products for the following reaction? Your turn. And I'll help you out. Hopefully you know this for tomorrow, but in case you haven't done a lot of studying, I'll help you out. And while you're doing that, I need another bottle of water, so I'll be back in a minute or so. Good news. Full bottle, ready to go, nice and cold. Fire me up. All right. Let's find out if you're done or not. If you're finished early, please be patient. Try and give everybody time to finish. Finish. All right, let's get going. Now, if I look at this molecule, I'll look for what's different. What's not a carbon-carbon single bond? Oh, a double bond. And oh, a second double bond. And notice they're separated by more than one carbon. So they act like they're alone. But because I have not one, but two double bonds, I need extra water. You don't need extra catalyst in order to make sure I don't have to balance it, which is why I put excess there. Now, double bond, acid and water, you break the pi bond, one carbon gets the hydrogen, the other gets the hydroxyl group, and it follows Markov-Nikov's rule. Now, do you break carbon-carbon single bonds? No. So I start out with 6 carbons. I better end up with 6 carbons. Now, when they're separated by more than one carbon, which I'll always do for you, each double bond acts like it's alone. So if we look at the first double bond, this has 2 hydrogens, the double hydrogens on double bond. This has 1, which is more, this. So the hydrogen, following Markov-Nikov's rule, will go this way. Remember, water is HOH, and the hydroxyl group will go here. Now, if we look at this double bond, this has 2 hydrogens, that has 1, which is more. Hopefully you took 2. So the hydrogen will go here. That's an ugly looking arrow. The hydrogen will go to the carbon with the most hydrogens on that double bond, which is here. And the other carbon will get this hydroxyl group. And now I know there are 4 bonds to carbon. And I'm done. So remember, when you have more than one double bond separated like that, each one reacts like it's alone. but it's still in the same molecule. And remember, do you break carbon-carbon single bonds? No. All right, one other thing while I'm on a roll here. What would be the starting material used to react with bromine, Br2, to make this? Now, I'm going to help you out, but tomorrow you shouldn't be helping yourself out. You should be memorizing these. And it's your turn. What would you react with bromine gas, Br2, to make that molecule? And we'll do, when you're done, give me a thumbs up. And you keep my mouth closed too. Give me a thumbs up. Uh-oh, it's Bad Humor Wednesday. Look out. Oh, wait. I made a mistake. My brain's on. I think it's time for me to almost give up. I'm sorry, I made a mistake here. Let's do this again. Once in a while, I even get brain freeze. And this reaction is still good hint. Sorry, that happens once in a while. Very rarely, thank goodness. As they say, oops. Hopefully I don't have to say too much the rest of the semester. Oops. And when you're done, give me a thumbs up, because now you can do it. Anybody done yet? Thank you, Jordan. Thank you, Jimmy. And we'll wait for your other two colleagues to finish. Oh, good news. I always proof my test a couple of times to make sure I don't do a oops problem. All right, we gotta get going because our time is almost done. How do you do this problem? You look at what you're trying to make. This, look for what's different, what's not carbon, what's not hydrogen. Ooh, not one, but two halogens, bromine, on adjacent carbons. Adjacent means right next to each other. And we show halogens like this. And this is bromine gas. And we have X2. What do we react? A double bond. And remember, X can be fluorine, chlorine, bromine, which it is, or iodine. And the two carbons, in this case, going backward, that had the halogen, are the two carbons in the double bond. Now, do we break carbon-carbon single bonds? No. So we end up with a six-membered ring. We have to start with one. And the two carbons with the halogen will be the two carbons right here in the double bond. Let me redraw that so it looks nicer. And there you go. And that's how you do it. Again, look for what's different. Think about it in a general term, two carbons adjacent with halogens. And then what do you react with? This one is starting materials to make the other one a double bond. And you go backwards and you know you don't break carbon-carbon single bonds. And if I look at the clock, boy, time flies when we're having fun with organic chemistry and Dr. White. Boy, where does this afternoon go? I hope it goes quick for you. All right, listen up. Tomorrow after class, I will send out the password for test number 1. You'll have until Friday, 11 a.m. I'll mention tomorrow, but by Sunday, 1 p.m., hopefully a lot earlier, I will post in D2L your final grade. I'll also have emailed out the points that you get for each question you answer on test number 1. And I will also go over on Monday the answers to test number 1. But tomorrow I'll be doing it after class. And don't forget tonight, if you need help, I have my office hour. And with that, I'll say, gang gesund, be healthy. Bye.